All right, let's jump right into this explainer. We're going on a pretty incredible journey today, tracing energy all the way from the macro world of moving giant objects right down to the microscopic realm of heat transfer. Energy is, quite literally, the ability to do work. But as we're about to see, how it gets transferred, how it transforms, and how it's conserved makes for one of the most fascinating stories in all of physics. So I want to hook your brain right away by challenging your everyday definition of work. Picture this. You're helping a buddy move and you are carrying a massive heavy flat-screen TV in a perfectly straight line across their living room at a constant speed. Are you doing work? I mean, in everyday language, absolutely. You're sweating, your arms are shaking, your muscles ache. But in the realm of physics, the answer is probably going to surprise you.
Here's our roadmap for today. We're looking at work and power, kinetic and potential energy, conservation of energy, specific heat, and finally heat transfer. Let's get right to it.
Stop number 1. Work and power, and how science actually defines them.
Okay, here is the official scientific breakdown. Work requires applying a force over a distance, but specifically in the exact direction that the force is applied. The formula is simply work equals force times distance. So here's the crazy part about carrying that heavy TV or say a heavy rock across a lawn at a constant speed. It isn't actually work in the physics sense. No way, right? But think about it. You aren't applying a forward force to keep it moving at a constant velocity. You're only applying an upward force just to hold it against gravity. Since your upward force and your forward movement are in totally different directions, zero scientific work is done. Now lifting it directly upwards off the floor, that is absolutely work because the force and the movement are going in the exact same direction.
And this brings us brilliantly to the concept of power. Power is simply the rate at which you do that work. Imagine two people trying to get identical TVs up to a fourth-floor apartment. Person A sets up a slick pulley system and hoists it up there in 2 minutes. Person B just toughs it out, carrying it up the stairs, taking 5 minutes. Because those TVs have the exact same mass and go up the exact same vertical distance, both people do the exact same amount of work, but person A generates way more power because they get the whole shebang done in less time. By the way, we measure this power in watts, named after the famous inventor James Watt.
Let's do a quick pause check here, just to make sure this is really clicking. Say you're at the gym, and you hold a 200-Newton barbell perfectly still over your head for 5 agonizing minutes. How much work are you doing? Well, think about our equation. Work equals force times distance. The immediate reasoning here is that you're doing exactly 0 work. Why? Because the distance moved is 0. It really doesn't matter how exhausted your muscles feel. No distance means 0 scientific work.
Moving right along to Section 2, kinetic and potential energy, or the energy of motion.
Mechanical energy basically comes in 2 main flavors, kinetic and potential. Kinetic energy is all about motion. If an object is moving, it has kinetic energy, and how much it has depends on its mass and its velocity. Potential energy, on the other hand, is stored energy. If you apply a force to lift a rock, the work you put in gives that rock gravitational potential energy. The higher you lift it, the more energy it stores up. And the split second you drop it, gravity accelerates it downward, immediately transforming that stored potential energy directly into the kinetic energy of motion.
This builds perfectly into one of the most unbreakable rules of the universe in Section 3, conservation of energy, featuring the roller coaster ride.
If we look at a roller coaster, we can clearly see this law in action. In a closed system, assuming we ignore pesky things like air resistance and friction for a second, total mechanical energy is strictly conserved. It's like a giant cosmic bank account where the balance never changes. The energy just constantly swaps back and forth between potential and kinetic forms. At the very top of the highest hill, right before the drop, the car has maximum potential energy and pretty much 0 kinetic energy. As it rushes down the slope, it loses height but gains speed, so potential energy converts directly into kinetic energy. Hit the absolute bottom of the valley, and your potential energy is basically 0, while your kinetic energy is maxed out. The total amount of energy, though, never changed.
Time for another quick pause check. Let's apply this unbreakable rule. If a falling rock loses 500 joules of potential energy on its way down, how much kinetic energy does it gain, assuming no air resistance? The immediate reasoning dictates it gains exactly 500 joules of kinetic energy. Energy is never simply lost, and it's never destroyed. It is only transferred or transformed. The books always balance.
But you know what happens when we do include friction? This truck example perfectly bridges our explainer from the mechanical world over to the thermal world. Picture a massive 10,000-kilogram truck riding the brakes down a steep 75-meter hill at a constant speed. It's losing a tremendous amount of potential energy,
But because its speed is completely constant, it isn't gaining any kinetic energy. So where on Earth does all that energy go? It transforms into internal energy inside the brakes. That mechanical energy, keeping the truck from speeding out of control, transforms into intense heat, sometimes literally boiling the brake fluid.
And that heat perfectly sets up Section 4, specific heat, comparing water and land.
Because heating things up definitely isn't a one-size-fits-all kind of deal. Every material absorbs energy differently, and this is dictated by a property called specific heat. By definition, it's the amount of heat necessary to change the temperature of 1 kilogram of a substance by exactly 1 degree Celsius. You actually have a really intuitive understanding of this if you've ever spent a summer day at the beach. Have you ever noticed how the dry sand can absolutely scorch your bare feet while the ocean water right next to it remains freezing cold? And yet, they've both been sitting under the exact same sun all day long.
Let's put some real numbers to this. Think about water-specific heat. It's a massive 4186 joules per kilogram degree Celsius. Now compare that to glass at just 840 or copper all the way down at 387. It requires roughly 5 times as much heat to raise the temperature of water compared to glass. Water can just absorb a tremendous amount of energy with very little resulting temperature change. This single property is exactly why coastal climates are so much milder than landlocked cities. The ocean acts like a giant thermal battery, storing up massive amounts of heat during hot weather and releasing it super gradually when it gets cold.
And that leads us to our fifth and final section, heat transfer, or how all this energy actually moves around.
So there are 3 fundamental ways heat gets around: conduction, convection, and radiation. And amazingly, they can all happen at the exact same time. Think about a classic fireplace in a cozy room. The fire heats the room by pulling hot air up the chimney draft. That's convection. It heats the brick hearth it's sitting on. That's conduction. And the glowing embers warm your face from all the way across the room. That's radiation. Let's break these down a bit more.
First up, conduction. It's all about direct physical contact. If 2 things touch, the faster-moving molecules of the hot object literally crash into the slower molecules of the cold object, transferring that kinetic energy. We feel conduction in action right in our homes. If you step out of bed, your bare feet feel freezing on a kitchen tile floor, but totally fine on a fuzzy carpet. The tile isn't actually at a lower temperature than the carpet. It feels colder because tile is a much better conductor. It's literally pulling or conducting the thermal energy away from your body much faster than the insulating carpet does.
Then we have radiation, which is wild because it needs 0 physical contact, traveling entirely via electromagnetic waves. And the rate of this heat transfer depends really heavily on color. Black objects are the most effective absorbers and radiators of heat, while white objects are poor absorbers, acting almost like little mirrors bouncing the radiation away. This perfectly explains why a freshly paved black asphalt parking lot will roast your feet on a summer day, while the green grass right next to it stays relatively cool.
Okay, let's do a super quick recap of our energy journey today. We started by proving that scientific work absolutely requires moving an object over a distance. We then tracked how mechanical energy effortlessly transforms between motion and height on a roller coaster, always remaining conserved in a closed system. And finally, we uncovered the invisible pathways of heat transfer, showing how everything from the smoking brakes on a truck to the sand on a beach handles thermal energy differently.
Before I let you go, I want to leave you with this transfer question to really test your new knowledge. If a space probe is coasting through the complete vacuum of outer space, which of the 3 methods of heat transfer is the only way it can lose its internal heat? Remember, space is empty. It completely lacks physical matter to touch, so conduction is out. It lacks fluids or air to flow, so convection is out. That leaves only one incredible method. So how does a hot object cool down out there in the absolute dark? Hint, think about how the sun reaches us here on Earth. Thanks for hanging out with me for this explainer, and keep looking for the amazing physics happening all around you.